So I'm going to talk briefly and at a somewhat high level about some adventures that we've had over the past few years in trying to understand, in some sense, what makes naturally occurring optimization problems easy. So we're going to talk a lot about non-convex optimization. With this as a topic, I'm grateful to Eric for the beautiful talk that we just heard. His talk laid out this very nice and very unified program of approaching different machine learning and data science tasks and sort of formulating them as optimization problems in a unified fashion. He also closed with this very nice quote that essentially asserted that the study of physics is largely the study of symmetry. And so we're going to continue on both of those themes, maybe from a little bit of a different perspective. We're going to talk about some simple non-convex problems, far simpler than anything that we've seen at this conference so far, simple enough that we can make some clear mathematical statements about them. And we're going to try to understand why they're easy, right? We're going to understand why non-convex optimization is tractable in practice. And it's going to turn out that when we look under the hood, when we study these problems, actually the study of this question boils down to a study of symmetry. So symmetry, which we heard about to some extent in the last talk, is going to rear its head again here. Okay, so before I get started, this is joint work with many folks, Yutian Zhang, Qing Chu, Ju Sun, a number of former students and collaborators. We'll mention folks as we go. As I said, the broad question in this talk is, we all understand that optimization is critical to the practice of statistics, signal processing, AI, if you will. And we also know that some of the most important, most interesting, and most practically relevant optimization problems that we encounter in these domains are non-convex. And, of course, when I talk about non-convex, I should just note, since, maybe we have a mixed audience, convex means bowl-shaped, right? Easy to ski down to the bottom. Non-convex is everything else. And that's kind of the challenge, that when we start thinking about non-convexity, when we start thinking about the general classes of problems that we have to solve, if we want to, realize some of these very beautiful ideas, we immediately run into the difficulty that optimization in general is impossible, right? Optimization is NP-hard in general. And in particular, non-convex optimization in the absence of bowl-shaped structure is hard. And it's easy to quote hardness results from the literature, but the difficulties here are kind of obvious. They're the kind of things that you think about the first time that you write down an optimization problem, right? If you let me do whatever I want, I can pretty easily formulate problems that have many spurious local minimizers, right? So bad local minimizers are a potential problem. Also, maybe a more subtle source of potential hardness, although one that we do occasionally have to contend with in practice, is this possibility of writing down objective functions that are so flat that it's hard to find a good direction to move, right? So as I'm sure many of us are aware, optimization algorithms are fairly nearsighted, right? All they're going to do is to look at the geometry of the function in a neighborhood. And so if that neighborhood doesn't give me strong information about which way to go, it may be the case that even if the problem has no spurious minimizers, I still can't efficiently make it to a minimizer. Okay, so these are two geometric obstructions to optimization in general and to non-convex optimization in particular. All right, so what I like to do when I talk about this topic, with apologies to Zhou Chen and to others who have heard a version of this talk before, is I like to start with an experiment. And at the time that we first ran this experiment, it was kind of surprising to me. Now, in light of the direction that the field has gone, this may seem like very simple stuff. And in fact, it is. This is far like worlds less sophisticated than what we saw in the previous talk and what we've seen in other talks in this conference. But I still like to show this experiment for two reasons. One is to give us a reference point for the phenomenon that we're going to talk about. We're going to really see it happening. And I think that's important because the theory in this area is still developing. We'll allude to some mathematical results, but the proofs are long and kind of complicated, and there's really a lot that we don't know. So I want to show this just to get us all on the same page and to set the tone that there's really a real phenomenon here that's deserving of mathematical study. So the setting here is kind of a baby representation learning problem. What I'm going to do is I'm going to try to learn a concise representation for this picture. So the way I do it, now here we're going back maybe 10 or 15 years. The way I do it is I take the picture, I chunk it up into some small patches, and now I'm going to try to learn a concise representation for those patches. So I put the patches as columns of a matrix, we call it Y here, and then I'm going to try to approximate this thing in a similar style to JPEG image compression or wavelet-based image compression. I'm going to try to compress this thing by expressing these patches as combinations of some basic building blocks. So mathematically, this is going to correspond to looking for a factorization of a matrix. I have a data matrix Y. I'd like to write Y is Q times X. Here, the columns of Q are my basic building blocks. They're my so-called dictionary. And because I want a simple representation, I'm going to ask for the X here to be sparse. Okay, so this is my setup. I have a data set. I'm going to try to concisely approximate it. And of course, at this point, we know very well how to do that. We set up a big optimization problem where I basically just write down what I want in this representation. I want to well approximate the given data, and I want the representation to be sparse. Data fidelity, L1 norm. Now, here, because I'm learning for a single image, I'm going to restrict my dictionary a little bit. So I'm not going to allow too many building blocks. So here, kind of similar to wavelet-based image compression, I'm going to ask that my representation Q be an orthogonal matrix. Okay, so Q is a square matrix with orthonormal columns. And that's it. I'm just going to try to write Y is Q times X. Okay, so this is an optimization problem, right? There are two groups of variables. There's a Q and an X. I have a constraint. One of the first things that we can note about this problem is that any reasonable formulation of this data representation problem is going to be non-convex. And that non-convexity comes from a very simple place. That non-convexity actually comes from the symmetries of the problem. I'm trying to find some building blocks, visualized here as the dictionary Q, that can well approximate a given data set. What matters in forming this approximation is not the order in which I record those building blocks. What matters is what they can represent. So if I was to take my dictionary Q and just permute its columns, I would get something that's just as good, right? I can represent the data set just as well, just as sparsely, just as accurately. So there's a permutation symmetry in this problem. Now, this problem, the symmetry structure is relatively simple, right? There's just this single permutation symmetry, reordering the columns. But, of course, if you work with more modern machine learning architectures, you know that this issue is ubiquitous, right? Like a neural network is this writ large with symmetries at each layer. Okay, now, what does that symmetry do to the geometry of optimization? Well, it means that if I have a single good solution, if I have the best representation, that's going to be a global minimizer if I've done a good job of formulating the problem. And so is its permuted version over here, its permuted version over here, its permuted version over here. So, somehow for every target solution, I actually have combinatorially many equivalent solutions. Now, this might not be a big deal. These are all equally good from the perspective of the task, but it certainly means that we're going to have to contend with a pretty complicated geometry in solving this problem and in thinking about why we can solve this problem, right? It's certainly not convex. Okay, now, fortunately, 10 to 20 years of practice in signal processing and machine learning and related areas has suggested that maybe we don't need to worry so much about that, right? There's a tried and true approach to attempting to solve problems that look like this one, the one that I showed you. And that's to randomly choose a starting point and then iteratively minimize the objective function until I'm roughly satisfied with the result. And it happens that this particular objective that I've written down here for technical reasons is amenable to alternating directions. You can optimize it with respect to Q with X fixed. You can optimize it with respect to X with Q fixed. Both of these can be done efficiently in closed form. But that's basically the idea. I pick a random starting point and I bounce back and forth between the Q and the X until I'm willing to call it a day. Okay, so what I'm going to do, just to frame the rest of the talk, because the rest of the talk is basically going to show you some pictures and some mathematical theorems about this problem and problems that look like it, is I want to show you this in action. So what I'm going to do is I'm actually going to give you, this is courting disaster here, but I'm going to give you a live demonstration. So let's go ahead and run this. So this is my picture. Here, this is the Golden Gate Bridge in San Francisco. What I'm showing in this graph is the objective function as a function of iteration, starting from a random initialization. So I start from my random initialization, I bounce back and forth, and after maybe 1,000 or so iterations, I hit something that might be a local minimizer. What's being plotted here in the graph is actually the representation that we learn. These are some of the little dictionary atoms. So you can see we started with this Golden Gate Bridge, which maybe has some linear structure. You can see some spots and bars here, maybe representing that kind of linear structure. Here, our emphasis is not so much on the properties of this representation. There are far more sophisticated things that one can do, but more on trying to understand what's going on with this optimization problem. So, again, what we've done is we've run it to completion once. In a second, once we get done rendering the dictionary here, we will go ahead and run it to completion again. I apologize. Somehow something always goes wrong. For some reason, this is rendering a little bit slowly. But in any case, there's the image. Here is objective function as a function of iteration. And in a second, once we plot just a few more of these things, we'll show you what happens if you do this from a new random starting point. Okay, so here we go. Here's our second run starting from a new random starting point. So you can see, there's some, if you're a connoisseur of optimization methods, there's some kind of interesting behavior here. Maybe you're passing by some sort of a critical point, right? It may stagnate at some point. But you'll notice that we hit the same final objective value. And again, here's a third run. starting from a new random initialization, we hit the same final objective value. And again, we hit the same final objective value. And if we were to go back and plot the same figure for each of these runs, actually what we would see is that we're finding the same representation of the data up to this intrinsic symmetry in the problem. So somehow, although this is a non-convex optimization problem, it seems like that's not hurting us too much. At least we're always finding solutions of the same objective value. Perhaps we're even finding globally optimal solutions. Okay, and so the question is, well, what's going on here, right? We have this inherited kind of pessimistic picture of optimization in general. Here, we formulated an optimization problem solely based on our desires, not with any real attention to tractability or solvability, and we seem to be getting away with it quite nicely. And I think as many of the folks on this call know, this is not the only place where this happens, right? This seems to be a fairly general phenomenon that we can be fairly aggressive about formulating very sophisticated optimization problems, including problems that live in classes that are hard in the worst case. And we can do quite well in practice when computing on practical data. Okay, and so I don't know how to explain that phenomenon in great generality. This talk is going to be an attempt to just encapsulate a few things that we've learned over the past few years by looking at relatively simple non-convex problems. There's a literature that has developed around this type of question. And what this literature suggests is that for the non-convex optimization problems that are simple enough for us to understand analytically, for the ones that are simple enough that we can really sink our teeth into them, it turns out that there's a really critical role of the symmetry structure of the problem in shaping the optimization landscape. In some sense, these symmetries that I described earlier are not just a nuisance or some ancillary feature of the problem. Actually, this plays a primary role in dictating how these things act as optimization problems, and in some cases, why you can solve them globally. And so we're going to look at a few non-convex problems through the lens of symmetry. I'm going to focus on a few things that my collaborators and I have done in the past few years, and then we'll sort of tie it together with a broader picture at the end. Now, when we talk about non-convex optimization, it's worth just pausing briefly to reference the one non-convex problem that everyone can solve, and everyone solves almost every day if you're a numerical person. This is actually, for those of you on the call who are students, this is a really great exercise to sort of get you into this literature and get you thinking about these types of problems. And so the exercise is, consider the problem of optimizing a quadratic form over the sphere. So you're going to minimize x transpose ax subject to norm of x22 is equal to 1. And now the task is prove that every local minimizer is global for that problem. Okay, so what you do is you write down the derivative of that quadratic function. I guess that's twice ax. And you realize that to be a critical point, that thing needs to be normal to the sphere. So what that's going to imply is that the critical points of this simple problem are actually eigenvectors of the symmetric matrix A. And moreover, you can understand the curvature of the objective function. You can understand whether they're minimizers, maximizers, or saddle points simply by looking at which eigenvalue those eigenvectors correspond to. Okay, so you do a little bit of calculation, you take second derivatives over the sphere, and what it's going to show you is something very intuitive, that the local minimizers, every critical point is an eigenvector. Local minimizers are tail eigenvectors. local maximizers are lead eigenvectors. Everything in between is a saddle point, and the number of directions of negative curvature is just the number of smaller eigenvalues. Okay, so what does it tell us about this problem? You know, obviously, this is an important technical subproblem, and this phenomenon is actually really important to sort of why we can decompose matrices efficiently and so on and so forth, but it's not something that we directly care about. Well, it says that in this particular case, we've avoided these two obstructions to global non-convex optimization, right? Local minimizers are global. Saddle points have directions of negative curvature. And this example is nice because you can sort of prove it with a couple of lines of algebra. Okay, so the eigenvector problem is an example of this phenomenon. Now, I'll say for Zhou-Chen and for the experts, as I go through the talk, I only have about 15 more minutes. I'm just going, maybe even less, I'm just going to show you some pictures, show how the phenomena play out geometrically. I'll allude to theorems. Those theorems come with concrete analyses of algorithms. Those concrete analyses of algorithms basically hinge on making these statements quantitative. So, you know, you sort of prove that at every point, either you have a strong slope, so you're not going to get stuck, or you have negative curvature, so you're highly unlikely to get stuck. You're going to fall off in one way or the other, or you're near one of the points that you like. And by making these phenomena quantitative, we can, for example, prove convergence rates of methods, analyze number of iterations, prove that the problems are solvable in polynomial time, all of this. For myself, that's intellectually important, but it's not the really interesting and beautiful thing. The interesting and beautiful thing is that these kinds of things work at all. And so what we're going to be interested in here for this talk is more the geometry that enables that. So we'll sort of sweep some of this under the rug. Okay, so let's move to an example that's, you know, just an inch closer to the practice of machine learning and signal processing. So this is a baby version of the baby representation learning problem that we looked at earlier. This was a data representation problem where I tried to factor a matrix into a dictionary and some coefficients. So we want to understand the structure of this type of problem mathematically. That's a really tall order. It turns out that there's not a lot that we know structurally about these kinds of problems. And so one device that people use to get started doing theory is to sort of assume, for the sake of doing analysis, that there is a true dictionary out there in the world, and I'm trying to recover it. So I'm going to assume that there's a true Q and a true X, and my goal is to find them. And that makes life a little bit easier because I can make some assumptions on them. So the assumptions that I'm going to make, one of them is a big restriction. As we did in the experiment, I'm going to ask the dictionary to be an orthogonal matrix, right? At least it's going to be square and invertible. The other is more of a technical convenience. I'm going to assume that the X that I'm trying to recover is a sparse random matrix. Okay, so this is the model under which the technical analysis is going to proceed. Now, I mentioned this is a baby problem, right? I'm going to dial it back even a little bit more to maybe an infant problem, a very simple problem. In order to make some pictures and write some theorems, I'm going to think not about the problem of recovering the dictionary as a whole, of finding the whole Q. I'm going to think just about the problem of finding one of those basic building blocks. And it's going to turn out that that's enough. That then, you know, based on that, I can give provable methods and I can think about more holistic approaches. But this is going to let us make some pictures and do some math. So the original problem was one of sparsifying something over the orthogonal group. Now the problem is going to become one of sparsifying something over a sphere, right? If Q was originally an orthogonal matrix, its, its columns are orthonormal. Now, one of those columns has unit L2 norm. So I have a problem where I'm optimizing something like an L1 norm over a sphere. Okay, and this is what that might look like. So here's the sphere. I've plotted the objective function over the sphere. Here, lighter means bigger. So the yellow points are maximizers. You can see there are a lot of maximizers. The red points are those target solutions. So this is reflecting in some sense the symmetry structure of the problem, that we have all of these different target solutions. And you can see a couple of things here. One is you can see that this problem has a pretty rich geometry. If you go looking, you'll find a large number of critical points. In particular, this problem has an exponential number of saddle points. On the other hand, that geometry is pretty regular. And to see how this comes through, one way that I like to visualize this is actually in coordinates. So here I'm plotting the objective function as a height. So here, those red points are these equivalent solutions that we started talking about at the beginning, these sort of symmetric solutions. And what you can see is that this is very much not a convex function, right? There's a very rich collection of critical points. On the other hand, it has a very regular geometry. It's almost like someone has taken a concave function and then symmetrized it in this kind of very regular manner. And in particular, and this is something that you can prove, although we won't emphasize the details in this talk, it's pretty easy to believe that if I start at any point on this landscape, I just plop down a randomly initialized gradient descent method, kind of like we did in the experiment, that, it may take an interesting path, but it's very likely to ski down to one of these red points, one of these target solutions, and not get stuck along the way. And in particular, in this picture at least, there are no spurious local minimizers, and you can see this at the maximizers, and you can also see this at the saddles. Every non-minimizing critical point has a direction of strict negative curvature. And that direction of strict negative curvature is not an accident of the problem formulation. It's actually a consequence of symmetry, namely that those directions of negative curvature that ensure that we don't stagnate, that we don't get stuck, are actually directions that break the symmetry between two equivalent solutions. They go, for example, from one of these red points to another. So no spurious local minimizers, negative curvature and symmetry breaking directions. And for this problem, at least, the symmetry structure pretty much tells you what you need to know about the optimization problem. Of course, actually making that mathematically precise is a lot of work. You assume a random model, you do some technical analysis, you use concentration of measure to prove that if you've seen enough data, then this thing behaves regularly. And you get out of this mathematical theorems that more or less say that if the problem is sparse enough and if you've seen enough data, then this nice geometric picture obtains, not just in the graph, but it actually obtains with high probability in whatever dimension you would like. Okay, and so that's the sort of theoretical claim. So if you're interested in theoretical claims, there's a long paper that works out all of the details of this. This is sort of interesting for the theory of dictionary learning if you care about that area. If not, the major takeaway here is that the high-level phenomenon is very simple, right? There's a symmetry structure on the problem, and that actually makes this a nice non-convex problem that we can solve globally. Okay, and this is, you can use these ideas to actually learn dictionaries. This is showing that. Okay, so, that's a simple example. It's somewhat close to the problem that we started the lecture with. I can see that actually I'm already over time. I guess we're running a little bit behind schedule. So I'm going to take the liberty of talking briefly about one more problem, which is kind of a convolutional version of what we just saw. And then we'll try to tie things together with a bigger picture at the end, talk about some open problems. So the second problem that I'd like to touch on briefly actually comes from a collaboration with a group in physics at Columbia. So these folks are interested in understanding novel and exotic materials, in particular what are known as high temperature superconductors. They do that using electron microscopy, which is an incredible imaging modality. That's another talk all to its own. For our purposes, I see there's a question. Okay, thanks. So Yijun Liu asks, sorry, I missed it, but it is that symmetry in the first example comes from the restriction that Q is orthogonal. So good, that's an excellent question. So in the first problem, there's always going to be a symmetry structure unless you do very artificial things. The particular signed permutation symmetry does come from the restriction that Q is orthogonal. That's a general feature of these types of problems. Whenever you sort of have a prior that's applying element-wise, like sparsity, you typically get a permutation symmetry, right? There are also permutation symmetries in non-negative matrix factorization and in ICA and in a number of related data representations. If you drop the orthogonality constraints, you don't get rid of symmetry. Actually, the symmetry group becomes bigger. Then instead of an orthogonal symmetry, you might have something like a general linear symmetry where you can put an invertible matrix and its inverse in between instead of just putting a permutation in between. Okay, so sure, yeah, no problem. And I know we have a formal Q&A structure, but if there are other questions, feel free to put them in the chat. Okay, so with that said, so the second class of problems that I'd like to talk about briefly, again, is motivated by this application in physics, trying to understand the properties of crazy and exotic materials. What this problem boils down to from a sort of data representation perspective is, again, just finding basic building blocks for pictures. This device gives you a picture. Actually, the way that these folks operate it, it gives you not a picture, but a sequence of pictures. So it's like a data cube. And that data cube contains some interesting events. These correspond to dopants or impurities in the material. These are what give it its properties. And you don't know where those events are, and you don't know what happens in the material at those events. So you have a data model where your data set is basically a superposition of little motifs. And your task as the data analyst is to find those motifs and diagnose where they occur in the material. And of course, this is a style of problem that shows up throughout the analysis of scientific data. This is a style of problem that shows up in neuroscience, like spike sorting and other microscopy modalities. But we sort of ran into it through this interaction with the BAAI. So I can kind of see this as a convolutional version of what we just showed you, right? I have a data set, and I would like to represent it as a superposition of some basic building blocks, except those basic building blocks are now going to be stamped down at different places in space. So this is some kind of a convolution, right? The motif signatures with a sparse map that tells you where they happen. So instead of Q times X, here you have Q, or we've written it as A convolved with X. Okay, and deconvolution is a very old problem in signal processing. There are 70 something years of work, a lot of different models. The particular model that's relevant here is what's called a short and sparse model. This is also the one that makes sense for most scientific applications. Short in the sense that the little motifs are small compared to the sample as a whole, sparse in the sense that they show up hopefully at relatively few points. Okay, so this is the setup. All right. And, again, at this point, there's not a lot of ambiguity in how to convert a problem like this into an optimization problem. Following what we saw in the previous example, I'm going to minimize some combination of fidelity to the data, right, an approximation error, and fidelity to the model, some kind of sparsity. Probably the only interesting part in the formulation that's on the slide is the constraint. I'm going to ask, kind of like we asked Q to be orthogonal or to be on a sphere when we boiled down to a single one, here I'm going to ask my motif to have unit L2 norm. And it actually turns out, if you look under the hood, that choice matters a lot for the geometry of optimization. So remember, we said that it's very important that we have negative curvature in symmetry breaking directions, right? Things are not too flat. In convex optimization, positive curvature is your friend. In non-convex optimization, negative curvature is your friend. Negative curvature prevents you from getting stuck. And it's going to turn out mathematically that the curvature of the problem as an optimization problem over a sphere or over an orthogonal group is really generated by the interaction between the curvature of the objective function and the curvature of the space over which you formulate the problem. So this sphere constraint kind of seems like very boring throwaway, but it's actually really important for getting the right geometry. And the theory gives you some sense of why that's the case. Okay, but in any case, this is the formulation. Now, instead of a permutation symmetry, we have a shift symmetry, right? In the sense that if I think about A convolved with X, if I shift A to the left and I shift X to the right by the same amount, they convolve to the same thing. So what was a permutation symmetry in the dictionary learning problem now becomes a shift symmetry in this deconvolution problem. And of course, if you have multiple motifs, then you also have a permutation symmetry on top of this. Okay, so this is, I think in the interest of time, I won't show you an experiment for this one. I'll just say that we see a pretty similar phenomenon, right? You write down a natural algorithm, you throw it at the data, and it finds the right thing. And it finds the right thing in situations where sort of eyeballing the data or using your favorite hand-designed transform doesn't. What's interesting for this talk is really how the symmetries of this problem affect the geometry of optimization. And so, again, to capture this mathematically, we have to mutilate the problem a little bit. We make some pretty aggressive assumptions. In the interest of time, I won't go into them in too much detail, but happy to talk in the Q&A, or you can look at the paper. Basically, we assume that the spike train is random, and we assume that A is shift incoherent. What that means is that these shifted copies of it are not too close together on the sphere. And so, if you go to do theory, then you get sort of trade-offs between the extent to which A is nice and X is nice and so on and so forth. Okay, but basically we make some assumptions. And we get to a formulation that, kind of like the dictionary learning is not exactly the same as the one that we started out with, but which, again, provably works. This is what it looks like. So this is plotting the objective function near a single symmetric solution. Again, this is in the vicinity of a single shift of the ground truth. You see this nice bowl-shaped structure, right? Convex function. Now, if I look in the span of two shifts of the ground truth, again, you see this nice negative curvature due to symmetry, right? I have a minimizer near each of those equivalent solutions, And in between, I have curvature that means that essentially no matter where I start, I'm going to find one of those two nice solutions. And so on and so forth. Same in high dimensions. In high dimensions, I get this kind of egg carton-like structure where I have different equivalent solutions, which are minimizers, and in between, everything just kind of follows from symmetry. I have negative curvature in the directions that break the symmetry, and that's it. So, you know, again, there's this, it's certainly not convex, but there's this beautiful geometry to it that suggests that you're going to be able to do well here. Okay, and again, this is something that one can make mathematically precise if you've seen enough data. If the problem is nice enough, then you can prove a theorem that tells you that this happens and tells you that you can find that target solution algorithmically. Okay, so I think I'll skip the comparison to the literature on deconvolution because again, you know, if you're an enthusiast of that area, you can read the paper and you can compare. I will say that this idea of just putting it on a sphere so the geometry is right and getting the optimization right actually does surprisingly well in practical deconvolution. You can beat a lot of things that make much fancier assumptions about the structure of natural images. Also, getting the domain of optimization right, understanding the geometry of optimization is helpful for enforcing your prior knowledge. This is an example from calcium imaging, you know, spiking behavior in the brain. And again, if you get the geometry right, then you have a lever for sort of sensibly using prior information about the motifs and the spikes. Okay, so I'm way over time. What I'd like to do is just to conclude with a little bit of a unifying picture. We talked about some nice non-convex problems where we have this slogan, you know, symmetry in the problem leads to easy geometry, leads to global solutions. It turns out if you want to think about what's been happening in this area over the past few years, you can roughly organize things according to the symmetry group. So there are problems like matrix completion and recovery, robust PCA, so-called linear neural networks that exhibit continuous symmetries. The symmetry group is something like an orthogonal group. These problems actually all exhibit the same topology of critical points and a very similar geometry. These are problems where often we have good convex relaxations, but they're computationally unwieldy. Thinking about non-convexity gives us a lever to scale to bigger problems. Okay, so that's for continuous symmetries. This is just a canonical example of that, the generalized phase retrieval problem. What we've shown are two examples of problems with discrete symmetries. These also tend to have similar topology, right? So dictionary learning problems, certain tensor decomposition problems, deconvolution problems, you always get a kind of version of this characteristic geometric structure. And I'll say a lot of the interesting action and the interesting unknowns in this area, you know, if you're a young person who's looking for something to work on, a lot of the interesting questions are here under discrete symmetries. How do we think about multi-layer neural networks? There's a lot that's open there. How do we think about more realistic versions of the phase recovery problem that I alluded to earlier? There's a lot that's open there. And also for these problems with discrete symmetries, usually convex relaxation fails. So these are problems where we really legitimately need to be non-convex and we need better understanding. So there are some interesting specific open problems. One that just gets at this question of theory versus practice and worst case versus typical case is the behavior of randomly initialized gradient descent. I talked earlier about this issue of spurious local minimizers and flat saddle points. It turns out that if you look at the class of optimization problems that have no flat saddle points, across that class of optimization problems, randomly initialized gradient descent is actually not efficient. You can come up with these kind of fun examples. This is work of Simon Du and collaborators at left here. These kind of fun examples where you can basically trap randomly initialized gradient descent by having saddle points that feed into saddle points that feed into saddle points in a kind of adversarial way. So that's the worst case. It actually turns out that what we run into in practice is often a lot closer to the best case. So in something like this dictionary learning problem, which I show at Wright, rather than having concentration about the stable manifold, rather than things tending to stagnate and get stuck, there's actually a global structure to the critical points where negative curvature upstream actually helps you to escape downstream. And so because of this, for these types of problems, randomly initialized gradient descent actually is efficient. And you can prove this mathematically. Delineating the boundaries is interesting, maybe not so much for theory of gradient descent, but it's really important for understanding what family of optimization problems we're actually encountering when we go to do optimization in practical data science, machine learning, and so on and so forth. Okay, so thank you all for attending the talk. I think I'll just close by thanking my collaborators. Thanks to the organizers, Shuicheng, Zhouchen, and everyone. I really appreciate the opportunity to speak. Here are a few references. And if we have time, I would be very happy to take questions.
Okay, John, thank you very much for so many very beautiful results. Yeah, so let's just take one question from Professor Lin Zhouchen. Yeah, Zhouchen, please.
Hi, John. Nice to have you here. I want to ask, your symmetry is in the sense that the objective function has some pieces that look similar, but there's another sense of symmetry, which means that if your input is transformed, then the output will be transformed in a similar manner. So what's the relationship between these two sense of symmetries?
Yeah, thanks, Zhouchen. That's an excellent question. So I think, right, so Zhouchen raises this good point that here when I talk about symmetry, I'm talking about symmetries of the model or symmetries of the, which turn into symmetries of the optimization problem. But what about symmetries of the data? In particular, when we talk about training neural networks for image classification, for example, we always do data augmentation to account for the fact that the data are allowed to transform in certain ways, and we see that that helps performance. And how should that come into the picture? So first of all, I agree. Thinking about the structure of the data is really important, and I really like model problems that have some symmetry in the data, in particular as a lens for studying neural networks. There's kind of an elephant in the room in the first half of the talk, which is we talk about these very simple models, but of course, what everyone would really like to do is what Eric described, right? Everyone wants to be able to solve very sophisticated problems, and people are often solving those very sophisticated problems successfully in practice. And my own personal, not intellectually justified, but my own personal viewpoint on this is that if we want to do mathematical theory that helps to explain that, taking into account symmetries of the data is very interesting and very important. And we actually have a work in the pipe. That's what I was hoping to talk about here, but sometimes things take too long. Does that help, Zhouchen?
Yeah.
Yes.
Good.
Thank you very much.
Okay, John, Thank you very much. Yeah, so actually we still have some other questions. We will forward to you later and hope we can get some replies from you. Okay.
Yeah, I'll be happy. I'm sorry we didn't have time now. All right, thank you.
Thank you very much.